if we know the coordinate vector of an element of a vector space with respect to one basis, and we want to find the coordinate vector of that same element with respect to a different basis, then we can move from one coordinate vector to the other by multiplying by an appropriate matrix. In particular, if bases let's say B is V1 through Vn and C is W1 through Wn of a vector space V are related by B equals Cp, now P here is an n by n matrix. So filled with numbers, and I'm thinking of B as sort of a row vector of vectors and C as a row vector of vectors. So this means that V1 through Vn equals W1 through Wn times this matrix P. This is 1 by n, 1 by n, and n by n. Okay, so two bases are related that way. And the coordinate vector of some element V in the vector space with respect to B is A1 through AN, written as a column vector. Then the coordinate vector of V with respect to C is just P times the vector A1 through AN. The reason is that if V equals A1 V1 dot 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 AN VN, so that's what it means for the coordinate vector of V with respect to B to be A1 through AN. It means these are the coefficients, these are the multiples of the basis elements that we need to get V. Then V equals, we could write this as B A1 through AN. That is, B is this row vector of vectors, V1 through Vn, A1 through AN. And if B equals Cp, so if B and Cp are equal, then we can plug in Cp for B, and now V equals C times this whole thing is now the coordinate vector of V with respect to C. So that is V equals W1 through Wn, P A1 through AN. because W1 through WNP is just V1 through Vn. So now the question is, how do we find this matrix P which relates the two bases B and C this way? And the answer is, it's defined, well, let's see, first I should mention the book. This matrix P is written as P C left arrow B. I'm just going to write it as P for now. So the answer is that P is defined by the jth column of P is the coordinate vector of Vj with respect to C. So the reason is, if we write V1 through Vn equals W1 through Wn, and then maybe raise P up here. When we multiply matrices, we multiply, add, and then the answer of each one of those dot products, where our left hand does a horizontal vector and our right hand does a vertical vector, the answer goes in the place where that column and that row point. So this means that Vj equals W1 through Wn times the jth column of P. In other words, the jth column of P is precisely the linear combination of W1 through Wn that gives us Vj. It's the coordinate vector of Vj with respect to the basis W1 through Wn, which is C. Now that might look like a nice formula, although usually it's hard to find the coordinate vector of Vj with respect to C. It's easier to find the coordinate vector of Wj with respect to B. But that's okay, we can do that, and if we do that, we're finding the inverse matrix, and we can just invert afterward. So if B is a natural, let's say easy to work with basis, and C is more complicated, it is easier to compute the coordinate vectors of W1 through Wn with respect to B. That is, the equation B equals CP is equivalent to BP inverse equals C. If we multiply both sides on the right by P inverse, so then the jth column of P inverse is the coordinate vector of Wj with respect to B. And then we can always invert P inverse to get P. Alright, so for example, let's look at the polynomial that we looked at in the last video, and the same two bases, the natural basis and the other basis that was less natural. So V is the vector space of polynomials of degree less than or equal to 3. B is the natural basis (1x, x squared, x cubed), and C is an other basis. Not terrible, but not as nice as his natural basis. 1 plus x, 1 plus x plus x squared, and 1 plus x squared plus x cubed. P of x is 1 minus 3x squared plus 8x cubed, and the coordinate vector of P of x with respect to B is 1, negative 3, 0, 8. And we're wondering, what is the coordinate vector of P of x with respect to C? Well, BP inverse equals C, where the columns of P inverse are the coordinate vectors of 1, 1 plus x, 1 plus x squared, 1 plus x squared plus x cubed with respect to the natural basis 1x, x squared, x cubed. So that is, the coordinate vectors are 1 and all zeros, 2 1s and all zeros, 3 1s and a 0, and all 1s. So that means that P inverse equals 1 and all zeros, there's the first coordinate vector. 2 1s and all zeros, that's the second coordinate vector. 3 1s and a 0. And 4 1s. So the coordinate vector of Px with respect to C is capital P inverse times 1, negative 3, 0, 8. I'm sorry, it's P, which is P inverse inverse. So if we can find, we found P inverse, so we just invert this, that's going to be P. And this matrix is not so hard to invert because I put easy numbers in it. So to invert P inverse, we write P inverse next to the identity matrix, and then we do row operations until we find the identity matrix on the left-hand side of this augmented matrix. Alright, so this is already in row echelon form. We want to put it in reduced row echelon form. So we'll use this one in the 4, 4 position to clear out the entries above it. So row 1 will be row 1 minus row 4. Row 2 will be row 2 minus row 4. Row 3 will be row 3 minus row 4. And we get 1, 1, 1, 0. 1, 0, 0, negative 1, 0, 1, 1, 0, 0, 1, 0, negative 1, 0, 0, 1, 0, 0, 0, 1, negative 1, and then the last row just gets copied. Alright, so now we cleared out all the positions above the 1. And now we need to clear out all the positions above the 1 in position 3, 3. So row 1 becomes row 1 minus row 3. Row 2 becomes row 2 minus row 3. That'll clear out those two ones. And we get 1, 1, 0, 0, 1, 0, negative 1. And here negative 1 minus negative 1 is negative 1 plus 1, so that's 0. And then 0, 1, 0, 0. 1 minus 1 is 0. 0, 1, negative 1. And negative 1 minus negative 1 is negative 1 plus 1, which is 0. And then the third row just stays the same. 0, 0, 1, negative 1. 0, 0. Fourth row stays the same. Now we're almost done. We just need to get rid of this 1. And we can do that by taking first row becomes first row minus second row. And that gives us 1, 0, 0, 0. And over here 1, negative 1. Negative 1 minus negative 1 is negative 1 plus 1 again, which is 0. And then this, everything else stays the same. Zero, 1, negative 1, 0, 0, 0, 1, negative 1, 0, 0, 0, 1. So this matrix on the right hand side is P. Alright, and we wanted P times the vector 1, negative 3, 0, 8. So we have this written here already, and this is 1, negative 1, 0, 0, 0, 1, negative 1, 0, 0, 0, 1, negative 1, 0, 0, 0, 1, times 1, negative 3, 0, 8. Which is 1 plus 3 is 4. Negative 3 minus 0 is negative 3. 0 minus 8. And then 0, 0, 0, 8. Oh, that doesn't look like the same answer I got last time. I got 1, 3, negative 11, 8. Ah, I put the 0 in the wrong place. There's supposed to be a 0 here. So 1, 0, negative 3, 8. Now let's see what we get. 1 minus 0 is 1. Negative 1 times 3 is positive 3. And then negative 3 minus 8 is negative 11. And then we get 8 in the last position. Alright, that agrees with what I have in my notes. So this is the coordinate vector of, again, the coordinate vector of 1 minus 3x squared plus 8x cubed with respect to the basis 1, 1 plus x, 1 plus x squared, 1 plus x squared plus x cubed. The end.